Great pleasure to be here. So I'm going to talk about work that I was hoping will appear in September 2022, and it didn't. But then in September, I thought, well, it will appear in November, and it didn't. So then I thought it will appear in January, and okay. So I'm not going to tell you when it's going to appear, but like I really hope next week, and I don't know how realistic it is. So the paper is not out, but it's joint work with Daniel Carranza, whom I brought here all the way from MSRI, and then Zach Lindsey, whom I didn't bring all the way from Chicago for practical reasons. Okay, so what is it that I want to talk about? I'm going to actually go back in time a lot to 1967, to a book by Gabriel and Zisman, which was called Calculus of Fractions, and they have a different preference for capitalization than I do, so we'll stick to that, and homotopy theory. And so the book is from it's not that old, 1967. There are probably people in the room that know way more about it than I do, and I apologize to anyone whose intelligence I'm going to offend with my summary of what's in the book. But I actually want to spend the first half of the talk just talking about what they do in this book. So the original problem that they deal with is localization of categories. So the goal is understand localization of a category at a class of weak equivalences. Okay, so in order to make sense of that, we need the concept of a marked quasi-category. Marked category first. So a marked category is a category C with a class of maps W. Okay, that's the definition. And a few examples that I want to keep in mind are something like topological spaces with weak homotopy equivalences, or maybe simple shell sets with weak homotopy equivalences, or maybe just groupoids with equivalences of categories, or if you happen to be Daniel or Eric, the category of graphs, simple graphs with what people consider weak homotopy equivalences. And in fact, this is how this whole enterprise started for me and Daniel. Okay, so once we have such a thing, we want to consider its localization. So what is the localization? Definition: the localization of a marked category CW is a category, that's tricky, okay, CW inverse with an identity on objects functor gamma from C to CW inverse, and now this functor has to have the property that it inverts all maps from W, so such that gamma of W is contained in the isomorphisms of this category, and moreover, it is universal among such functors. And for any f from C to D, such that f of w is contained in isos, there is a unique f bar from C W inverse to D such that f bar composed with gamma is f. So in other words, if I have C, I have my localization functor C W inverse. Whenever I go by f with the property that f maps all the weak equivalences to isomorphisms here, there exists a unique extension over here. So I require a unique extension. And one way of saying what it does is, well, whenever I have a functor from C W inverse to D, I can, by precomposing with this thing, I can get a functor from C to D. And these are not any functors. These are some special functors, namely those that take weak equivalences to isomorphism. So these are functors f with the property that f of weak equivalences is contained in isos. And and what I'm going to require then is that this is a bijection. Okay, cool. So that's what the localization is supposed to be. And the first question, whenever you have some universal property, is whether this thing exists. And so the first theorem is, well, does it exist? And the answer is it does. So the localization always exists. Localization always exists. So how can we prove that? So we know what it has to be in some sense. So we know that this functor is identity on object. So what we're going to do is we're going to just take CW to have the same object as C, and then we just need to declare what the morphisms are. Morphisms are. So I need to tell you what a morphism from X to Y potentially is. But now I need to somehow invert all weak equivalences. So I'm going to take maps from C, and I'm going to take inverses from W. So what does that give me? Well, it doesn't give me a category if I just take the union. Well, simply because I need to figure out how to compose such things. So I'm just going to take arbitrary zigzags of that form, where I'm taking a map from X forward to something, but then I'm taking a weak equivalence back. Then I'm taking another map forward. I'm taking a weak equivalence back. And I continue like that. And then I can end with maybe weak equivalence from Y. OK, so that's so those morphisms are zigzags of that form. Zigzags like that. And a different way of saying it is that we just take a push out of categories. Or take push out in cat. So what do I need to do? Well, I'm going to take my category C, and now I need to invert weak equivalences. So I'm going to just take 1. So 1 is 0 less than or equal than 1. Pose it like that. And I'm going to take a disjoint union of those indexed by all the weak equivalences. And then I'm going to invert all of those guys. So I'm going to add inverses. So for me, E1 is the contractible groupoid on two objects. Now this just picks out all the maps that I need to invert. And I'm going to take a push out like that. So great. Unfortunately, push-outs of categories are just completely unworkable. So I don't really know what to do. So maybe let's use this board to recall. So first of all, we finished the proof, but now we can recognize the problem. So this is unworkable. And for instance, you can see that because those zigzags could go through any objects here, so this need not be locally small, even if C was. Yeah.
If one of the weak equivalences was the identity, then didn't I accidentally add an extra morphism, call it the inverse of?
Yes, I may need to be careful to avoid isomorphisms. Yeah.
Okay.
So let's take this push out at the. Actually, so you can just avoid isomorphism altogether, or you can see that in the push out, I think they'll cancel because you'll be quotienting by some equivalence relation somewhere. So, so yeah. But yeah, there is a way of describing it that would be more economical. Okay. Okay. So this is where we start. That this is completely unworkable because of these zigzags. And so the solution that Gabriel and Zisman are then proposing is use calculus of fractions. Calculus of fractions. So let me tell you what that is. So it's a condition on the pair CW that would make sure that this localization is somehow workable. So first, let's figure out what the condition is. So we say that CW satisfies calculus of left fractions. So, and this is really long, so we're going to abbreviate it to CLF. If, and now there are three conditions that we need to take care of. So the first condition is that W is a wide subcategory. So all the identities are in to be wide, and subcategory is closed under composition. 2, given a span of the form this, so I have some span in which one leg is a weak equivalence. We can complete it to a square of this form. So we're gonna now put the weak equivalence here and an ordinary map over here. And so it's a commutative square. And moreover, if this map was a weak equivalence, I also, so that means this map was a weak equivalence, I also demand that this map is a weak equivalence. So notice that I didn't assume any 2 out of 3 or any property like that. So I really need to impose this condition addition. Okay. And the third condition is that if in a diagram of that form, I have F, G, like that, with, so this is with, and not just a W. So FW is equal to GW. Then there is V such that VF is equal to VG. So in other words, if I can equalize things on the left by a weak equivalence, so this map is a weak equivalence, then I can also do it by a weak equivalence at the end. Okay, so these are 3 conditions that I need. And with that, we can...
There's a question.
Yes?
Does W have to contain all isos?
No, not necessarily. Not for this term. Yeah. So yeah, so it doesn't need to be a saturated class. It doesn't need to satisfy 2 out of 3. So I mean, in practice, right, like, so first of all, you don't need to invert weak equivalences. They're kind of already inverted, but yeah. Yeah, so we don't require that. Or to be more precise, Gabriel and Zisman don't require that. Because this is all their stuff. So the theorem that they then prove is that if CW satisfies CLF, then I can actually give you a much simpler description of the mapping space or the hom sets. So in the localization, stuff from X to Y is just a collection of fractions of length 2 subject to some equivalence relation. So I apologize for using tilde for pretty much anything that could be equivalence relation, similarity, or anything like that, but I just don't know that many other symbols. I'm not going to use this one. So we're pretty much stuck. OK, so what is the equivalence relation? So we're going to say that a fraction, so these are called fractions. And I don't know why, but they are called that. So we're going with it. So a fraction like that is related to a fraction like that, y double prime, let's say, if and only if there exists another fraction. So we're going to put all those fractions together. There's y. There are those weak equivalences. There's y prime, y double prime, and maybe there's z in the middle. And maps this way. Okay? And if it fits into this commutative triangle or a bunch of commutative triangles, so if there exists z like that, then I'm going to identify two fractions. OK. So this seems much shorter than those zigzags of arbitrary length that I had here. So let's just quickly take a second to see how I'm escaping the zigzag hell. Oh my goodness. I think I write too much on the board. I remember when I was a student, I was taking, I think the class was called sheaf theory, and the instructor would talk for 25 minutes and write one letter on the board, which was like, oh, and talk for 25 minutes about it. And I remember he would say then, you understand? And we will all be super confused, looking at him like we clearly don't. And he would say then, oh, don't pretend you don't understand. So, I mean, why did you ask, right? Clearly you knew the answer ahead of time. So, OK, so how do we prove that? Well, the first step will be using this condition 2. So if I have an arbitrary zigzag going through some y prime, then going to y, I somehow, first I need to define composition of such things, and also tell you why I can only get away with using fractions of length, or zigzags of length 2. Well, I'm going to use the second condition to exactly swap these things. Right? So this is what I'm using condition 2 to get a proper map over here, and then a weak equivalence over here. And I'm also using the fact that weak equivalences are now closed under composition to compose those two. And so that reduces arbitrary zigzags to zigzags of length 2. Well, then you have to show that this is, for instance, that gives you a well-defined operation and so on. This is where condition 3 will come in. But that's essentially what goes into this proof. OK, so, oh my God, I'm jumping through. OK, so it gets better, is the thing. It gets actually really good. So here is another theorem that they prove. And this is where you should get a little bit suspicious. So if CW satisfies CLF, then first gamma preserves finite colimits. Finite colimits. And 2, CW has all finite colimits that C does. Yeah, so there may be some colimits, so there may be some diagrams that are not in the image of this functor, and as long as they are of the correct shape, they still exist in this category. So this is amazing. Why would that be true? Well, we just need to look at the description of this category. So the thing is, again, that's going to be proof sketch. So if we look at what the mapping spaces are, if we don't like the description of this form, we can also write it as the colimit over the category of y down arrow w. So this is the subcategory of the slice category. So my notation for slice category is with the down arrow, but I know that this is not very common, or it is common in certain circles. Maybe it's a better way of saying it. Yeah, but this is the slice category, and we only take maps that are weak equivalences. So if I take the colimit over all maps from y to y prime, and then I'm just taking maps from C to y prime. Yeah, so that's the, if you take this thing, right, I'm taking colimit over weak equivalences like that, so maps that are in W, and of maps from X to Y prime. Okay, but now what you can show, well, using this wealth of markers, I can now show that this category is co-filtered, and that's essentially what goes into the proof. So this category being co-filtered, I can commute finite colimits with this, and that's essentially what goes into the proof. But at that point, you should get extremely suspicious. And why is that? Well, pretty much no homotopy categories have colimits. So, like, the reality is amazing, but it's just too good to be true. So, for instance, top is complete, and co-complete. But if I take top and I invert weak homotopy equivalences, well, this has almost no limits or colimits. Yeah, and I mean, it has like co-products and things like that. But what I get out of that is that topological spaces with weak homotopy equivalences does not satisfy the calculus of left fractions. Okay, so that's a bummer. And in general, all the kinds of homotopical settings, homotopical categories, or maybe homotopical structures, let's call them. Homotopical structures satisfy a homotopy version, homotopy CLF or CRF, but not a strict one. What that means is only for triangles or for squares like that would commute up to homotopy. And that is not enough, because as soon as you quotient by homotopy and you're hoping to use those results, there are no longer any colimits there to be preserved. So in some sense, if you want to study the homotopy theory of spaces, this result is not as useful. Where it is somewhat more useful is some kind of triangulated setting. So one of the results that Gabriel and Zisman prove is that if you have an abelian category and the class of weak equivalences satisfies both CLF and CRF, then the localization is again abelian. So you can see what they are going for, but yeah, it doesn't apply kind of verbatim to the study of topological spaces. And one other remark is that the mismatch that we have here is that we would be looking at limits and co-limits in the homotopy category. And these are not the interesting object, right? Like we are interested in homotopy limits or co-limits, not limits and co-limits in CW inverse. Okay, so it's kind of that's how we that's kind of my beef with this result, even though I think the theory is actually very beautiful. Okay.
Chris, before we go back to the next board, did we mean that y down W is filtered? So you can, like if you have the maps out of a co-limit of x's, that becomes co-limit of n.
Yes, I'm sorry. This one is filtered. Yes. Sorry. I had, yes. Yeah, that's right. That's right. This one is, yeah. Yes, I want a filtered co-limit. So the thing is that our intended application was of CRF. And okay, so I think I started my talk with the arrows going, like when I started writing notes, I started one way, then I had to go back and revert everything. I hope I caught it all, but thank you for catching the last man standing. Yeah, so this result is good, but it's kind of too good. And in some sense, from the point of view of understanding the localization of spaces, we can really learn from the Republican playbook. Thanks, Obama. That's not a statement. That's not a statement of my political affiliation here. Either way, as a Canadian, I don't really understand American politics, but it's. I kind of like the thanks for nothing kind of sentiment. At least that's what I understood the statement to mean. But then I don't understand anything about American politics, so I apologize if I misunderstood what this means. Okay, so now what? Well, the solution to, so I think I wrote solution right here to use calculus of fractions. And now the solution led to a problem. So we're going to have a solution to a solution. Okay, so we're going to go to infinity categories. Go to infinity categories, which for me means quasi-categories. Quasi-categories. But before I do that, maybe it's a good moment to just quickly pause and ask for questions. Because we kind of finished, we're done with the 60s. It's time to move on. So does anyone feel like we should do something before we move on from the 60s? Does any of it make sense? No? Sorry?
Should we pretend we don't understand?
Oh, okay, okay. Yeah, let's, okay. Okay, no, so if you do understand, then perfect. Yeah, I never know how I feel about all that stuff, because on the one hand, like it's like Gabriel Zisman is very classical stuff, but at the same time, I think I had like no idea that that was true, and it like shocked me when I learned that, and and then immediately you realize, oh, okay, like it's because it like never happens. So the question is, can we have something that happens? Okay, so let's go to quasi-categories, and again, people know, many people in this room know that stuff much better than I do, but just to fix a model, so quasi-category is a simplicial set. I don't know if you often see simplicial sets defined without talking about quasi-categories, but just in case it helps, let's fix our notation satisfying the inner horn filling. Okay. So what that means is I have the nk horn, I have the simplex. Well, for any map like that into X, there exists a lift, not necessarily unique, whenever 0 is between K and N strictly. So in other words, I can compose one simplices, but I cannot invert them. And I can compose all higher simplices. Okay, and now, just to state things in full generality, so I told you what a category is, so now I need to replace the second definition I had on the board, which was a marked category. So a marked, in fact, we can do it with simplicial sets. A marked simplicial set is a simplicial set with marking with a collection W of one simplices. Okay, so that's a marked simplicial set, and we will be interested in localization of such things. Okay, so right after I told you what a marked category was, I told you what the localization of such a gadget would be. So what is the localization? So the localization of a marked simplicial set X W. In fact, sorry, I'll make it a quasi-category just to make things slightly correct. That's one of the objectives here. I guess I'm inconsistent with my W's here, so let's make this one ugly too. So the localization is a simplicial set, which, well, unsurprisingly, I'm going to denote X W inverse, okay, with a functor X gamma to X W inverse. Oh my God, yes. Yes, is a quasi-category. Perfect, thank you. Together with a functor like that, such that gamma of W lands in equivalences, and we're going to use this space over here to explain what a weak equivalent, or what an equivalence is in a quasi-category. So it's a map delta 1 into X that factors through what I would call E1. So E1 here is, I'm just going to take the same E1 that I had before, but now I'm going to move the 1 from brackets here just to the exponent, and I'm going to take the nerf of this thing. So this is the simplicial set that I'm using. So in other words, you are an equivalence if you factor through something that has an inverse, if that makes sense. Okay, so it's a functor like that, and again, it needs to be universal among functors that do that. So such that gamma and, well, once again, I'm going to have the map from functors x w inverse to y, where y is a quasi-category. We're going to have a map like that given by precomposition with gamma. So we're going to go to functors from x to y. And again, I'm not going to take all functors from, or all simplicial maps from x to y. I'm going to take those. So these are those maps f x to y, such that f of anything in w lands in equivalences of y. Okay, I'm going to demand that this map between two simplicial set B is a categorical equivalence, meaning an equivalence in the Royal model structure. So whatever equivalence of quasi-categories is, this ought to be 1. Okay, so these are two quasi-categories, and I relax the condition so that it's not a bijection now. That would be kind of too strict, unnecessarily strict. This is now only a weak equivalence in the model structure for quasi-categories. So whatever an equivalence of quasi-categories is supposed to be. Okay, so that's the definition of the localization. And I think I explained all the words that I used in this definition. Oh. So the first theorem is exactly the theorem that I gave you last time. Okay. I think this is, doing. I think I'm writing too much. So we're gonna, for the rest of the talk, I'm just gonna write this and talk for 25 minutes. Okay, so the first theorem we're gonna prove is that the localization always exists. Localization always exists. And how are we gonna prove it? We're gonna give the exact same proof as before. Just because okay, I feel like I'm borrowing too many Republican talking points, but I'm a lazy immigrant, so I'm just going to do the same proof as before. So now we're going to take our quasi-category X, and inside of it we have all those weak equivalences. Okay, so we're going to add their inverses, E1. And hey, good news, push-outs of simplicial sets are easy. So we're going to take this push-out. We glued in all the inverses. That's easy. There's one tiny little problem, namely, then we need to fibrantly replace, right? And that's kind of where problems begin. So we take the push-out, and fibrantly replace.
A fibrant thing is a quasi-category.
Yeah, a quasi-category is, I'm so amazed, I don't think I can go on. Yeah, it's, wow, okay. Okay, and so, so the push-out of quasi-categories is not a quasi-category in general, so we need to do something crazy like fibrantly replace in the Royal model structure. But guess what that does? That makes it unworkable. So of course the same problem that we had for categories now returns. It's just instead of making the push-out hard, it makes the push-out of quasi-categories if you need to fibrantly replace. But okay, what is the solution? So finally, the solution to the solution to the solution, the solution to this problem now is calculus of fractions Oh, it feels so good to write in this part. For quasi-categories. So somehow all those solutions were forced on me. So before I tell you what calculus of fraction is, I need to define an intermediate object. So we're going to define two simplicial sets. In fact, infinitely many. They will be indexed by some numbers. So first we're going to define this. It's L indexed by n, k, and then it has a star. So this last spot is available for your add, I guess. But other than that, yeah, it's pretty much taken all around. So what is this? These are subsets of n that contain k. And this is a poset, and so maybe I won't be looking at it as a poset. I will be looking at the nerve of that poset, okay? So now it's a simplicial set, and then I'm going to have L and K inside of it. It's going to be a subset of it, which omits n. Okay, so let's look at what this thing does. So I have two favorites personally. So I have L21 embedding into L21 star. So let's draw this one first, since then we just remove some elements. Okay, so what are the subsets of the set with element 0, 1, 2 that contain 1? Well, there's 1, then there is 0, 1, then there's 1, 2, and then there is 0, 1, 2. Okay, and one other thing, I want to consider this as a marked set, so a marked simplicial set. So marked at, well, two subsets, so an inclusion here is an edge, and this edge is marked exactly when their maximums are the same. Max A0 is equal to max A1. So in this case, it's going to mean that this is a weak equivalence, and I believe this is a weak equivalence, and there are no further weak equivalences. 1 is max, 1 is max, 2 is max, 2 is max. Now here, I'm going to remove the whole thing. So this means that I'm going to get 1 here, 0, 1 here with a weak equivalence, and 1, 2 here. Okay. And then the other one I need to be looking at is L22 embedding into L22 star. So now I'm going to take 2, embedding into 0, 2, embedding into 1, 2, and then all of that mapping to 0, 1, 2. These are all the subsets that contain 2. And now what is a weak equivalence? Everything is a weak equivalence. And then once again, I can remove the last, the top element, and I'm going to get 0, 2 with a weak equivalence, and 1, 2 with a weak equivalence. Okay. So why am I telling you about all those things? Because now I can state the definition of calculus of fractions. So xw satisfies CLF if 1. So the first thing I'm going to require is that W is weakly closed under composition. And I'll explain what that means, closed under composition. So whenever I have two 1 simplices, FG, composable, that are in W, well, I know that there will always exist some 2 simplex that witnesses that, or gives me the composite. Now I require that there exists some such two-simplex for which this is a weak equivalence. So strongly closed under composition would mean that for any two-simplex that has those two as those two parts of the boundary, this is a weak equivalence, but I'm only demanding that there is some such two-simplex. So this replaces my condition, actually, sorry, I should say this is 1A, and then I need to know 1B, W contains all degeneracies. And then I have 2 plus 3. So this replaces the wide subcategory condition, whereas I'm going to here replace conditions 2 or 3. So this is not condition 5. This is replacement for conditions 2 and 3 in the original CLF. Namely, that if I have marked maps from L and K like that, I can always complete them to maps like that. Okay, and if you remember what I required for my calculus of fractions, it was exactly completing diagrams like this, and then if the two things were weak equivalences, then those two things had to be weak equivalences. So having lived of that form is exactly calculus of fractions. So here I'm requiring that 0 be less than k, less than or equal than n. Okay, so this is the replacement for calculus of fractions, and just sanity check. And that's perhaps surprising that C, a category C, satisfies CLF as a category if and only if the nerf of C satisfies CLF as an infinity category. So somehow, for the nerves of categories, I can get infinitely many conditions. Like this direction to me seems clear, and in fact the proof is much easier. This direction is more surprising because remember there were only 3 conditions here, but now I'm getting this infinite hierarchy of conditions, but somehow all of them can be obtained by from just CLF. Okay, so we're not doing something completely crazy. So now I just have to tell you, well, now I want to prove the theorem that Gabriel and Zisman prove. But there's a question, like what do you replace? Like we need some replacement for higher simplices, right? Like in dimension 1, these were like just fractions. What happens in higher dimensions? So this is where we're going to talk about subdivision. And I know that I'm out of time, but I really want to tell you very quickly what is happening here. So we have this co-simplicial object SD plus, so this is marked as D, that goes to marked simplicial sets. So maps of marked simplicial sets are simplicial maps that also preserve the chosen edges. And what SD plus does is at n, we're going to take subsets of n such that A is not empty. Okay, so if we look at n equal 0, what we're going to get is just 0. If we look at n equal to 1, what we're going to get is something that looks like this, 0, 0, 1, and 1. And again, I'm marking them as using max. So A0 to A1 is marked if and only if maximum of A0 is equal to the maximum of A1. Okay, so this is marked, and then n equal to 2 will give me a picture that looks like this. Okay. Oh, sorry, this has to go to the center. So this is 0, 0, 1, 1, 1, 2, 2, 0, 1, 2, 0, 2, and equivalences go like this, given by max. And you can kind of see that this is exactly how I would like to compose fractions, right? I use calculus of fractions to swap this like if I want to compose this fraction with this fraction, I use calculus of fractions to swap those two, get this, and then I just correct to get a single fraction of that form. Okay, so with that definition, we can now define the marked x functor. So x plus is going to be something that will take a marked simplicial set to, well, we're going to take maps of marked simplicial sets from SD plus n. So this is these are the n simplices of it into xw. Okay, so we're taking a hum like that. And so we're really picking out diagrams inside of X that look like this. Moreover, we have a map. We have a map max from SD plus n down to n, which, given a subset, picks out its maximum, which gives a map maximum star from x down to x plus of xw. And now here comes our theorem. So the first thing is if xw satisfies CLF, then max from x, or max star, from x to x plus xw is the localization. So I found like a very small model for localization. But then we can further say a few other nice things. Okay, my conclusion is that your markers are just awesome. But that is bad for the board. The board suffers. But yeah, I have not seen a marker that strong in my lifetime, I feel like. So if, moreover, W is strongly closed under composition, so for every such tomorphism under composition, then max star preserves finite colimits. And 2, x plus is going to be xw has whatever finite colimits x had. Okay, so I'm realizing I'm way, way, way out of time. So I'll finish by saying some concluding remarks, maybe just without writing. So the first thing is that now these are the correct colimits. These are the homotopy colimits that we wanted. So the localization now we can conclude has, for instance, finite homotopy colimits whenever the category X itself had colimits. So that's that kind of reconciles the two frameworks. Now the other thing is, in particular, you can use it to find localizations of one categories at weak equivalences that give you infinity categories rather than one categories, and that remember this important homotopical information. The second big thing is that this holds in practice a lot. So whenever your weak equivalences are created, sorry, I want simplicial sets. So will be, so one big class of examples is if you have a finite column preserving functors, preserving map between quasi-categories, preserving map, and you define weak equivalences to be the pre-image of equivalences. So whenever you're in a situation that maybe you have a structured homotopy type, something, some infinity topos, let's say, and it has an underlying homotopy type, then defining equivalences via this gives you something that satisfies CLF, and so our theorem applies. And then in particular, if you have reflective localization, so something given by left adjoint that preserves all colimits, not just finite ones, that applies. So all the reflective localizations of higher topos theory are an example of this theorem via CLF. And there are many other connections, many other applications of this theorem that we found, but I guess I have like no time to say anything about them, so I'm going to stop here.
Any questions? Can you say how that condition with the LNs gives you the V's turn into W's turn into V's thing?
Ah,
Parallel on the left.
Daniel.
So I don't remember the exact cube that does it, or I don't remember the exact diagram that does it, but it would be an L32, I believe.
Yeah, it's one of the three cubes.
And what is a strongly closed under?
Right. So whenever you have F, G, and then arbitrary two simplex here, if this is a weak equivalence and this is a weak equivalence, then it follows that this is a weak equivalence. So for weakly closed, I only demand that there is some two simplex for which, right, like since, but again, this is kind of a condition you would expect, right? Because any two composites are homotopic. So if you're homotopic to a weak equivalence, you should be homotopic. You should be a weak equivalence, and yeah. But it turns out that for just this part of the theorem, you actually you only need weakly closed, and then strongly closed only enters to tell you something about colimits. So I guess maybe I shouldn't get into this distinction at all, but it's kind of cool that in practice, it's like in practice every class of weak equivalences that you can think of will be 2 out of 3 closed interval. But it's more of an exercise in full generality. Oh, sorry.
Okay, you mentioned the reflective localizations. Are model categories also always examples of this? Because you can take like cofibrant objects, and then probably the cofibrant objects allow this calculus of fractions?
Well,
I'm not actually sure, but it feels like.
So I can tell you exactly what happens in if you say restrict to cofibrant objects, then you have the notion of left homotopy, right? Where like you say the two maps x to y are equal or are homotopic, left homotopic, if so they give you a map like this, fg from the coproduct to y, and then this embeds into the cylinder on x, and there exists an extension like this. So this is your notion of left homotopy. And you can form the category, kind of the naive homotopy category, pi c. So here the objects are all the cofibrant objects, and you quotient by the relation of being left homotopic. So this now satisfies CLF. But if you want, so this satisfies the classical CLF, and then you can show that if you do the infinity localization, right, so you localize the class of homotopy equivalences, then you're going to get this.
But then it's not obvious that pi c has infinity categorical equivalence to begin with?
Yeah, so the other thing is like if you just localize from the start at weak equivalences, then you're really talking about the, so weak equivalences in the infinity localization become just weak equivalences, or become equivalences. So the only thing we're saying is that the category localized at equivalences, its own equivalences, if you want to invert isomorphisms, you didn't do anything.
Well, but I was thinking of taking the nerve first.
Yeah, so then you can compute the localization this way, yes. But so then you have to go through this thing, right? Like, so there is still like this slight mismatch. But yeah, one other thing, I guess one other thing is that like, if you take W to be, just equivalences here, then this map ends up being an equivalence in the Royale model structure because you inverted nothing, right? So it follows from this theorem. So it's kind of a special case that you need to prove the general case.